Hey everybody, it's Mr. Carr again. Today we're going to be looking at 3-1 day 2. So we talked before about what are exponential functions and their graphs. Today we're going to be solving problems using both exponential growth and decay. So pretty much all of these are going to be some kind of context to them. The first kind of context we're going to talk about is what's called compounding interest. So a compounding interest is when you are like investing money and you're earning interest, but instead of doing it one time at the end of the year, it might happen more times throughout the year. So for example, if the principal P, that's your initial investment, it has an annual interest rate of R. So this R value here is whatever it is. So it's like 5%. You write it as a decimal. So that'd be like, so if R is like 0.05 means 5%. Okay. That's what that's referring to in there. It gets compounded N times a year. So this N is what can change, and there's a variety of there. So like for, let's say it's compounded monthly, that means that N is equal to 12 because that's 12 months in a year. Let's say it's done weekly. N is then 52 because if it's done once a week over the course of a year, it's done like that. Okay. So it's just, you got to read that carefully and figure out what N is based on that. Okay. And then the balance A is how much will be in the account after T years. So let's take a look at one of these problems here. So Mrs. Salzman invested $2,000 into an educational account for her daughter when she was an infant. The account has a 5% interest rate. So $2,000 is our principal. We have 5% there, so that's R is equal to 0.05. If Mrs. Talsman does not make any other deposits or withdrawals, what will the account balance be after 18 years? So T is going to equal to 18. And then we're going to look at three cases. What happens if it's compounded quarterly, monthly, and daily? So if it's compounded quarterly, that means it's going to happen 4 times a year. Monthly, let me change the color on that one. So it'll be 12 times a year. And then daily would be 365 times. So we're going to set up this same equation 3 different times based on these different compounds. But the only thing that's going to change is N. So we'll start with our quarterly. So here's for reference here. The amount that's going to be in the account is equal to principal, which is $2,000 times 1 plus 0.05 divided by, in this case, quarterly, so it'll be divided by 4. And that'll be raised to the 4 times T power. Okay. So the next one, the amount that's in the account will be $2,000, 1 plus my interest rate of 0.05, but now it's going to be divided by 12, raised to the 12 T power. And for my last one, the amount that will be in the account is going to be $2,000, 1 plus 0.05, but divided by 365 and raised to the 365T. Okay. So what's happening with a compounding interest is the idea is that with an annual rate, if it's an annual rate compounded quarterly, the quarterly is going to happen at a smaller amount, but it happens 4 times a year instead of one time at the 5% at the end. Week or monthly happening once a month. Okay. So instead of doing it 5% one time at the end of the year, it splits it up into 12 smaller chunks, but it happens more often. So we're going to take a look at what happens when we calculate all these out for a time of 18 years. So we've got 2,000 times 1 plus 0.05 over 4 raised to the 4 times 18 power. So I'm just going to do that as its own thing right now, make it 72. Okay, so I'm simply just going to add this or put this in my calculator and multiply it all out. So we got 2,000 times 0.05 divided by 4 raised to the 72 power. And that's going to come out to 4,891.84. So $4,891.84. So $2,000 turned into that. If it's compounded monthly, okay, so it'll be 2,000, 1 plus 0.05 over 12, raised to the 12 times 18 power. That'll be 216. So real quick, what these mean, that means how many times it's getting compounded. So in the course of 18 years, this model will be compounded 72 total times. But this one's going to be compounded 216 times. Okay, so let's see what happens when we get that new amount here. Okay, so we got that. That'll be $4,910.02. So Compounding it monthly gives you a little bit more money than the quarterly does. And let's take a look at daily. So it'll be $2,000, 1 plus 0.05 over 365. And we can do 365 times the 18. That'll be 6,570 for that new exponent. So go ahead and plug that in. 6,570. And there we go. We got $4,918.90. Okay, so that's where the models will differ. So if you compound more often, you'll get a higher amount every time. So this also leads to our continuous compound interest. So continuous compounding is going to be a little bit different. We're still going to use annual interest rate R, but we're going to use E. Okay, E is a part of this one. So it just has a different model to it because this is, instead of saying it one time at the end of the day, it's just always compounding, always earning interest is the idea. Okay, so there's a proof for where this comes from. Not worth what we're going to talk about, so you can check that out on your own on that one. So for our purposes, we're going to look at same situation. Mrs. Salzman found an account, paid 5% interest compounded continuously on her $2,000 investment. What will be after 18 years? So just like before, we got this one right here. The amount will be $2,000 multiplied by E raised to the R, so it'll be 0.05 times T. That's my formula. So we're going to go ahead and change the T out for an 18. So 2,000 times E, 18 times 0.05 will give us E to the 0.9 power. So then I can take that 2,000 times, E raised to the 0.9 power there gives me 4,919.21. Okay, so technically that was a little bit more than the previous one. The daily, you see how close it is. It's $1 more. So not a big difference, but it does make it enough of a difference where we want to make sure we analyze that separately from the other types. Okay, the other types of models we'll have is going to be similar in our definitions here. We're going to look at a growth rate versus decay rate, as well as continuous growth and continuous decay. So growth is going to follow this pattern. This is actually very similar to the compounding interest one. The difference is we don't have to take R divided out. Okay, so if we're dealing with an initial amount, we'll call it n sub 0. And then we have 1 plus R. R is going to either be the growth rate or the decay rate. If the R value is greater than 0, that means it's a growth rate. Okay, if it's less than 0, so you are losing a certain amount, that's a decay rate now. So the idea is that you're going to take 1 minus a value. Here's what happens to this 1 plus R. If 1 plus R is greater than 1, we have growth. If 1 plus R is less than 1, we get decay. That's what's going to happen in our formulas. Okay. T is going to be the time, and time could change. So it all depends on whatever the scenario is given. So just make sure you're following along that. So maybe it's like growing monthly or it's growing yearly. Just make sure that T is matched up to that part. Continuous growth and decay, very similar setup to our continuously compounding interest. So we have KT here. So anytime that K is greater than 0, that's going to be our growth rate. So again, if it's increasing by a certain percent, that's what goes there. But if it's decay, that's going to be a negative number is what we're saying here. So for example, maybe it's like, we'll say 100 multiplied by E to the 0.05 T. This is something that's going to be growing by 5%. If it's decaying by 5%, it'll be a negative 0.05 T. So that's the difference how they look. Okay, so we'll get decay with a negative decimal rate out there versus positive growth. So let's look at these models here. The state's population is declining, it's a key word there, at a rate of 2.6% annually. The state currently has a population of approximately 11 million people. The population continues to decline at this rate. Predict the population of the state in 15 and 30 years. So the first thing is, because it's referring to it annually and not continuously, we are going to use this side of the model. Okay, so we look at what's our initial amount. We have initial population of 11 million. instead of writing out 11 million, yeah, I'm going to go ahead and simplify it and just make it an 11 there instead of having to write it all out. Yeah, so we'll just say 11, excuse me. Just be aware that when I put 11 there, that's referring to 11 million. So we got n sub 0 is 11. Our rate is 0.026. And we got t, two scenarios. T is 15 and t is 30. Okay, so that means my first model will be n is equal to 11 million times, let's see here. Sorry, 1 plus 0.026 raised to the t power. Well, so this is my overall model. 1 plus 0.026 to the t. And then we're going to evaluate it twice. So we're going to look at what happens when 11 times 1 plus, I can simplify it a little bit. It's just going to be 1.026 raised to the 15th power. And 11 times 1.026 raised to the 30th power. Oh, I just realized I made a mistake there. It was declining. Let's go back and take care of that. I'm sorry. It's declining it, so r is there, but it's actually going to be subtraction inside here. So those numbers are going to change. It's going to be 1 minus 0.026. Sorry about that. So 1 minus 0.026. If I write that new decimal number, it's 0.974. Okay, so after 15 years, I'm going to have 11 times 0.974 raised to the 15th power. And that's going to give me 7.4. Okay, so in this case, that's going to be 7.4 million people after 15 years. Do the same thing with 30. And that population will be 4.99 million people. Okay, so that's going to be my populations if it continues on this declining rate. Now, when we look at this one, we are declining, the rate's declining continuously now. So the state currently has a population of 11 million. What happens after 15 and 30 years at a continuously declining rate? So that means we're going to use this one. We got to find that keyword continuously. So in this case, K, if it's declining, is a negative 0.026. So my formula is going to look like this. My N is equal to my initial amount, 11, times E raised to the negative 0.026 times T. So again, we're going to do two different ones. We're going to do 15 and 30 years. So my first one is 11 times E to the negative 0.026 times 11 times 15. And then the same thing, E to the negative 0.026 times 30. Okay, so make sure you multiply the exponents out first before you raise E to that power. But I'm just going to put it all in my calculator at once. So 11 times E raised to the negative 0.026 times 15 is going to give me 7.45 million people here. And then same thing with 30. I'm going to get 5.04 million people after 30 years of continuously decaying or continuously declining. Okay, one more scenario to look at, and that's where we're going to have to build a model first. So table shows the population growth of deer in a forest from 2000 to 2010. The number of deer is increasing at an exponential rate. Identify the rate of increase and write an exponential equation to model this situation. Okay, so what's going to happen here is we are going to look at, first of all, this is going to be a time of 10 years. Okay, so I don't have it on here, so I'm going to model using this. It's growing, so it's going to be 1 plus R. Okay, so that's what we know it's going to look like there. So we're going to have the initial amount, which is 125. So that's 125 multiplied by 1 plus R, raised to the 10th power. So we don't know what R is yet, but we know that after 10 years of this compounding, not compounding, but this exponential growth, the total will come out to 264. So from here, the goal is to solve for R. Well, I can just undo a lot of steps here. For example, I can divide both sides by 125 to start. I do that, and I get about 2.112, and that equals 1 plus R to the 10th power. From there, we want to undo the 10th power. So we're actually going to do the 10th root to both sides. Okay. If I do that, I'm going to end up with 1.0776 for R. So what does this mean? My actual rate of increase is what this amount is that's after 1, basically. Remember, this is 1 plus r. Whoops, hold on a second. Made a mistake there. This would be 1 plus r. So the actual rate of increase, if I subtract 1 on both sides, it's going to be this. It'll be r is going to be 0.0776. So what does that mean? If I were to write it as a rate of increase, I could say that it is increasing by a rate of 7.76% per year. Okay, but what goes into the actual equation to write the equation out? So the number of deer here will be the initial amount, 125, times 1.0776 raised to the t power. Okay, so that's where we're going to get that model from. Now, to help us with that part, or sorry, to help us with this next part, we're going to go to the table. So let's use our graphing calculator and find this table here, because we want to use the model to predict how many years it will take for the number to reach 500. So we can see that it's going to keep growing. If it keeps growing by the same pattern, obviously going to go past 2010 like that. Give me 1 second. Okay, sorry about that. Just had to pause that. So we're going to go in and I'll go to Desmo so you can see how this table is going to look. So we know that in our scenario here, we've got 125 times 1.0776 raised to our x power. For here's the year 2000 is going to be 125. If I keep going up higher and higher, and let's see what happens like when we know we got to go past the 10, I should say. So if I can go start at 10 and go 11, okay, you can see that it's still growing a bit. We want to get up to 500. So I'm going to jump even further. Let's go 15. Okay, we can go maybe 20. There we go. So I know I've hit at least 500 there. So let's bring it back a little bit. 19, not yet. 18, there it is. So you can see here between 18 and 19, that's when we hit definitely from 479, passes 500, gets to 517. Okay, so using that table, we know that it will reach after between 18 and 19 years. So 18 to 19 years is when it reaches. So the question is how many years? Oh, yeah. So how many years? It'll happen between 18 and 19 years based on that table. So for now, that's just going to be our focus for finding that answer. Okay. And that's it. So again, we're looking at a handful of exponential growth and decay models, depending on if it's growing compounding interest or if it's compounding continuously. We get that using the value of E in there. And then also with our just any amounts, it doesn't have to be money related. And it could be continuously growing, continuously decaying, or growing and decaying by a certain amount per year. Okay, that's it for today. Take care, everyone.